Hello friends, welcome back to Rising Mathematics. In this video, we are going to solve question from linear algebra. Question is, let V and W are vector spaces over field F and T from V to W is 1-1 linear transformation. If V1, V2, Vn, these n vectors are linearly independent in vector space V, then the set TV1, TV2 up to so on TVn, these n vectors which are images of the above vectors in vector space W are linearly independent. So here we want to show that if T is a linear transformation from vector space V to vector space W and that linear transformation is a 1-1 linear transformation, then T will carry linearly independent vectors in V to linearly independent vectors in W. So before starting our proof, firstly we need to recall this definition. So if V is a vector space and V1, V2 up to so on Vn are vectors in V, we say that these vectors are linearly dependent over the field F if there exist elements say lambda 1, lambda 2 up to so on lambda n in field F, not all of them 0, such that the linear combination lambda 1 V1 plus lambda 2 V2 plus and so on plus lambda n Vn is equal to 0. Now, if the vectors V1, V2 up to so on Vn are not linearly dependent over field F, then we say that these vectors are linearly independent over field F. Next, we need to recall this theorem. Let V and W are vector spaces over field F and T from V to W is a linear transformation, then following are equivalent. First one is T is 1-1 and second thing is kernel of T is singleton 0. So let's start our proof. We have given that the vectors V1, V2 up to so on Vn are linearly independent in vector space V. Then according to definition of linearly independent vectors, for scalars lambda 1, lambda 2 up to so on lambda n in field F, if we consider this linear combination of n vectors Vn using these n scalars is equal to 0, then we must have all these n scalars should be equal to 0. Now we want to prove that these n vectors which are images of the given vectors in vector space W, these n vectors are also linearly independent in vector space W. So for this we will consider n scalars say lambda 1, lambda 2 up to so on lambda n such that this linear combination is equal to 0. Now since T is a linear transformation, using its properties, we can write this as T of alpha 1 V1 plus T of alpha 2 V2 plus and so on plus T of alpha n Vn is equal to 0. Again using properties of linear transformation, this can be written as T of alpha 1 V1 plus alpha 2 V2 plus and so on plus alpha n Vn is equal to 0. Now as image of this vector under T is 0, this vector must be in kernel of the linear transformation T. But we know that the given linear transformation T is 1-1. So using that theorem, we can say that kernel of T is 0. So as this vector is in kernel T, this vector should be equal to 0 vector. And this is the linear combination of these n linearly independent vectors with some n scalars. So as this linear combination is equal to 0, we must have these n scalars lambda alpha 1, alpha 2 up to so on alpha n is equal to 0. And as this n scalars comes out to be 0, when this linear combination we have considered it is equal to 0, we must have these n vectors tv1, tv2 up to so on tvn are linearly independent in vector space W, and this proves the given result.